In our last section of Chapter 12, we're going to be talking about something called colligative properties and the relationship to solutions. In this particular section, we're going to look at 4 different types of colligative properties. Colligative properties are those properties that are dependent on the amount of solute not just the type. We're going to come back around and look at molality, which is a new concentration unit that we learned about in this particular chapter, and its relationship to colligative properties. There are 4 different types of phenomena that we notice with the amount of solute or the colligative properties. The first is vapor pressure lowering, and I'll talk about all of these in more detail. Number 2 is freezing point depression. Number 3, boiling point elevation. And number 4, osmotic pressure. The normal boiling point of any substance is the temperature where vapor pressure is equal to atmospheric pressure. Now, standard pressure is 1 atmosphere. So as temperature increases, the vapor pressure inside a beaker or a test tube or whatever substance it is that you are boiling, as you heat it, as the temperature goes up, the vapor pressure is going to go up within this system. And when it becomes equivalent, then the substance is going to boil. And so that is an identification of a particular compound like water. All right, so one of the colligative properties that we notice is vapor pressure lowering. So what does that mean? If you look at this flask, you see the red solute molecules and the blue solvent. If something is soluble, it's going to share intermolecular forces with whatever solvent it is in. And so the addition of the solute will increase the intermolecular forces. So it requires more energy to make that phase change. In other words, there are less molecules in the vapor as there would be compared to the pure substance. And you see this, you can see the difference in the arrow in the beaker. That means that there is more in the liquid phase as compared to the gas phase. Here we have a phase diagram illustrating the next 2 colligative properties, freezing point depression and boiling point elevation. Right, so you see the freezing point depression shown in the red line. And the boiling point elevation likewise shown in red, and the pure substance is shown in blue. Again, this has to do with the intermolecular forces between the solute and the solvent. Another way to look at this too is it increases the distance in our phases. Okay, so let's say we have something that is in the liquid phase. Okay, so the shift is made down in temperature to lower when it's converted to ice, and at the same place, same viewpoint, the place where liquid is converted to gas is also pushed out. So it widens this range of phase changes. We'll do some calculations here in just a minute that allow us to calculate what these changes in temperatures will be. A common example of something that will impact a solution like water is antifreeze. And the active ingredient in most of these is ethylene glycol. Its Lewis structure looks like this. You see, it's an organic molecule. One thing that becomes apparent is that it has the ability to make hydrogen bonds. And so it will mix with water, make hydrogen bonds with water. And these intermolecular forces between the antifreeze and the water will lower the freezing point. That's good. Yes, and raise the boiling point. That's good because we don't want our car freezing or boiling over at easily attainable temperatures in the environment. So, particularly thinking about very cold temperatures that get down below zero, the antifreeze will prevent those fluids from freezing up. Before we look at the formula for freezing point depression and boiling point elevation, this a real interesting example from your textbook, this wood frog. It has the ability to hibernate. And can even survive partial freezing. The way it does this is by making and releasing a lot of glucose into its cells and extracellular fluids so that the glucose, as we know, glucose makes a lot of hydrogen bonds. And that is going to increase the number of intermolecular forces between the water that is inside the cell and outside the cell, along with the glucose. And so this will lower the freezing point. I'm going to erase for just a moment here, and we're going to talk about this formula. You see delta TF, and this the F, little f stands for freezing, is equal to molality times Kf, which is a constant. So each different solvent, or the common solvents, will have a Kf. Likewise, we could say delta TB is equal to molality times KB. And this is the difference of temperature in the boiling point. Same thing, molality, and this is the boiling point constant. There are two different things we have to consider, whether something has ions or not. So let me erase this other side over here. If there are ions dissolved or electrolytes dissolved in the solution, you have to consider the number of moles of ions. And that changes the formula just a little bit. It becomes delta TF is equal to molality times KF times I. And the I is the number of ions. I'll show some calculation examples in just a minute. One that's a non-electrolyte solution and one that is an electrolyte solution. Here are some constants. This is the KF and KB. For some common solvents, you can see water here, ethanol, carbon tetrachloride, some solvents that we've talked about before. Looking at water as an example, the normal freezing point, remember that's at 1 atmosphere pressure, is 0 degrees, and the normal boiling point is 100 degrees Celsius. The two constants, KF is 1.86 and KB is 0.512. And so what this should tell you is the solute's effect on phase change is more pronounced in the freezing point depression. Particularly for water. It's a mixed bag with some of the others. But in the case of water, the same amount of solute will cause greater reduction in freezing point as compared to boiling point. I made mention of electrolytes a moment ago. An electrolyte is defined as a solute that produces ions when dissolved in water. And this would be the common examples are shown over here on the chart. Sodium chloride, magnesium sulfate, magnesium chloride, potassium sulfate, and iron 3 chloride. A non-electrolyte does not produce ions, and so its I factor, or Van Hoff factor, is 1. So we don't have to put that in there when we're looking at the freezing point, depression, and boiling point elevation of a non-electrolyte. Right, so what does this mean as far as the number of ions? Sodium chloride, when it dissolves in water, dissolves into two components, the sodium, which is aqueous, sodium ion, plus the chloride ion, which is also aqueous. So the Van Hoff number is 2. Measure just tells you that there may be some equilibrium that is going on, so it's possible for not all of the salt to dissolve, but in most cases we'll just make the assumption that it is the number of ions. Right, and then if we look at something like potassium sulfate, K2SO4 solid, When this dissolves in water, we get 3 ions. We get 2 potassium and 1 polyatomic ion, sulfate. So the Van Hoff factor we would use is 3. The fourth colligative property is osmotic pressure. This is defined as the force that pushes water across a membrane when the solute concentration, I'll put that in brackets, is not equal for the two different things. Typically what happens is water will move through a membrane from an area of low concentration to an area of high concentration of some solute. So looking at the picture here, you can see on the left there's quite a bit of solute here, and we could just quantify it by counting it. But on the right hand side we've got pure water. So what's going to happen is that, and you have a semi-permeable membrane, which would be like a cell membrane. So water is going to move into the area that has the higher concentration of solute, or more solute particles dissolved. And so that's going to push water across that membrane. And when it does that, the side where the pure water was goes down, and the side where the more concentrated solution was is going to go up. Okay? So the difference between where that water line was before and after is the osmotic pressure. One place in biology where we see osmotic pressure and its effect on cells is consideration of red blood cells. In a normal system, there's going to be some concentration of sodium chloride, and I think off the top of my head it's 0.9%. And there's going to be glucose, typically, I think 5%, but I would have to go back and look at a biology textbook more exactly. The point is that there are some solute molecules dissolved. Okay, it's not pure water. Right, so in the case of normal red blood cells, an isoosmotic solution is one where the concentration of solutes inside and outside of the cell is equal. Okay, and I'll just draw sort of a crude cell there. A hyperosmotic solution is when the solutes outside the cell are greater than inside. So water is going to flow outside the cell, and it causes this crenation or shriveling. The third circumstance is an hypoosmotic solution, where the solutes inside cell are greater than the outside. So water is going to flow inside the cell and cause them to swell and maybe even rupture. Let's take a look at a couple of example problems where we calculate freezing point and boiling point of a solution. The first one that we'll look at is a non-electrolyte. And the formula, if you remember, is delta T is equal to molality times K. So first thing we need to find is the molar mass of glucose. And I'm just going to estimate here. 6 times 12 is 72 for each of the carbon. 12 times 1 for each hydrogen is 12. And 6 times 16 is 96. If we were to do it more precisely, it would be 180.18 grams per mole. I need to know the Kf. For water, it is 1.86 degrees Celsius per mole. And the Kb is 0.512 degrees Celsius per mole. We have 455 grams. And in the molality formula, you remember it's moles of solute divided by the mass of the solvent in kilograms. So this would be 0.455 kilograms. All right, we need to find molality, and then we can calculate both the freezing point and boiling point difference. All right. First thing, let's find moles of glucose. It's 55.8 grams, and 1 mole is 180.18 grams, equals 0.310 moles. Molality is 0.310 divided by 0.455. And we're getting 0.681 molal. Right, so let me erase some space over here for the second part of this calculation. Go ahead and leave those numbers down there that we need. Right, so delta TF equals 1.86 degrees Celsius per molal times 0.681 molal. So those will cancel out. 1.86 times 0.681 equals 1.27 degrees Celsius. All right, so instead of water freezing at 0 degrees centigrade, it would freeze at negative 1.3, negative 1.27 degrees Celsius. So you just subtract that from the normal freezing point. Likewise, delta TB, 0.512 degrees Celsius per molal times 0.681 mole equals in this case I'm getting 0.35 degrees Celsius. So the boiling point would go up to around 100.4 degrees Celsius. In our second example, we'll look at the boiling point of an electrolyte, boiling point and freezing point of an electrolyte solution. Okay, looking at potassium sulfide, solid going into water, we would have 2 potassium ions, AQ, plus a sulfide ion, AQ. So our I value, Van Hoff factor, would be equal to 3. We've already gotten molality, so we don't have to go through that calculation again. Calculating the freezing point would be 1.86 degrees Celsius per molal times 0.100 molal times 3 equals 0.558. So the new freezing point would be a negative 0.558 degrees Celsius. The change in temperature for the boiling point, 0.512 degrees Celsius per molal times 0.1 molal times 3 is equal to 0.154 degrees Celsius. So the new boiling point would be around 100.15 degrees Celsius. All right, we'll take a look at some more examples of freezing point and boiling point changes in class and practice these calculations.